S. Chan presents educational video lectures as per the AICTE curriculum. Difficult concepts made easy. Study anywhere, anytime.
In this part of the video, we will learn certain engineering applications of angular momentum, and we will be clubbing that topic with the help of mathematics.
If you want to study this topic in detail, refer to the book by S. Chan Publishing. Link is provided in the description box.
Welcome to S. Chand Academy, and I am Anmol Bhatia. We are learning the course which is engineering mechanics. Observe the video of a figure skater played on my right side, in which you will see that the figure skater will initially raise her or his hands, and after a moment of time the figure skater will collapse or bring the arms towards the chest. By doing so, the velocity of the figure skater increases. So what is the basic concept behind the same that we will be learning in today's part of the video. The course that we are covering is engineering mechanics, and the topics of the course is conservation of angular momentum, the Kepler's problem, and there are certain applications which is satellite maneuvers. So coming to the first part, which is conservation of angular momentum. So what is this angular momentum concept? So let's say if we have an external torque, and that external torque, if it is acting on a system, is 0, then the angular momentum is conserved. What does it mean? Mathematically, if this external torque is 0, then initial angular momentum is equal to the final angular momentum. That means the angular momentum remains conserved. This is the basically law of conservation of angular momentum. Here L indicates the angular momentum, and R and P indicates the linear momentum, and R indicates the position vector that we are concerned about. So we will see the derivation now. L indicates, as I have told you, that the angular momentum, and L is R cross P. So R is the position vector, P is the linear momentum. So when I have this position vector and the cross product of the linear momentum, I will get the angular momentum part. Now I need to find out the change of this angular momentum with respect to time. So what to do or how to do that? I need to derivate the same expression. So when I derivate it with respect to time, I will get dl by dt, that is equal to d by dt of r cross p. So what is this r cross p? It would be elaborated in terms of the product rule. So r remains the same, dp by dt, plus p remains the same, dr by dt, and cross remains as it is in this expression. So this dp by dt, as from the second law of motion, the rate of change of linear momentum is denoted by the force, and this dr by dt is velocity. Rate of change of the distance or the position vector is velocity. So velocity term was already there because of this momentum. So momentum is, linear momentum is mass multiplied by velocity. Velocity cross velocity would be 0. This is a term which is related to vectors. So v cross v is 0. So that means this angular momentum is equal to r cross p, wherein dl by dt is equal to tau. So an expression that we got is dl by dt equals to tau. That means initially I have told you that when this externally applied torque is 0, then the angular momentum is conserved. It means that when tau is 0, that means dl by dt is also 0. So when I integrate it, I will get L as a constant value. So L is constant, that means angular momentum remains conserved when this externally applied torque is 0. L has another formula which is I times omega, and linear momentum's formula, as you know, is mass multiplied by velocity. Here L indicates the angular momentum, I indicates the moment of inertia, and omega indicates the angular velocity. So L equals to I multiplied by omega is a newer formula of the angular momentum. So L equals to I into omega and P equals to mass into the velocity. Here in general aspect, moment of inertia is having this formula which is I equals to mr square. So omega is V by R generally. So when we substitute these formulas in this expression, I'll get L as mass into velocity into the distance, mass into velocity into the position vector of the same. So when I substitute this omega into this expression, I'll get omega as V by R, and I into this system, this equation, I'll get mr square. So R and R gets cancelled out, L becomes mv into R. So the formula of this angular momentum becomes L equals to mv into R. That means R would be the distance associated with the case. So let's say if we reduce the distance, so the velocity will no doubt increase so as to sustain this or so as to conserve this angular momentum. Now let's come back to that problem that we were discussing. The problem was of the figure skater, and the case was the figure skater joins his hands after a certain period of time, and ultimately the figure skater's velocity increases. So what is the case behind it? As you can see in the video, the figure skater when clubs or joins the hands, the radius decreases, and when the radius decreases, the velocity of the figure skater increases so as to get this angular momentum conserved. So this is the particular case related to the angular momentum aspect. Now as L equals to I into omega, I have told you the formula. When L is constant, that means this I omega, which is I1 omega 1 and I2 omega 2, both of them would be equal because your angular momentum is conserved. Now let us look at a numerical problem which is related to the angular momentum, and this problem I have taken from the book. So it says that when the angular velocity of the body changes from 20 radian per second, which is the angular velocity omega, and it changes from 20 to 40, so its angular momentum changes by 80 kg meter square per second. Find the change in kinetic energy of the rotation. So this is a numerical problem. So what data do we have? We have omega 1 which is 20 radian per second, omega 2 as 40 radian per second, and we know that this angular momentum is conserved. That means I1 omega 1 equals to I2 omega 2, and there is also a statement given that the angular momentum changes by 80 kg meter square per second. That means there is a change in angular momentum which is L2 minus L1 as 80. So I need to put in the value I omega 1 minus I omega 2, and what we can do, we can take this I part as common. Omega 1 is 40 and omega 2 is 20, so this becomes 20. So on solving, I comes out to be 4 kg meter square. And what was required in the question? It was required to find out the change in the kinetic energy. So half mv square, or you can say the formula for kinetic energy is half I omega square. So the first type of kinetic energy, or the kinetic energy in the first situation, would be half I omega 2 square minus half I omega 1 square. So what I can do, I can take half as common and I also as common. So I omega 2 square minus omega 1 square. So I is 4, omega 2 is 40 and omega 1 is 20. So I can substitute this value and I will get this final value of kinetic energy. So we stop here for a break, and what we have learnt in this topic we have learnt about a practical application of conservation of angular momentum, and also we have seen mathematically that why this figure skater joins his hands so as to increase the velocity. After coming from the break, we will learn the newer aspects which are related to the angular momentum.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back after the break. Before going to the break, we have learned certain concepts of angular momentum. Now we will be learning about the topic which is Kepler's laws and satellite maneuver, which is related to the same topic. So let us start the same. So the topic that we will be covering in this part would be the Kepler's laws of planetary motion. So there are basically three laws of Kepler's. So first law states that every planet revolving around the sun in the elliptical orbit, and the sun is at the focus. That means let's say this is the sun and this is the planet. So every planet is revolving around the sun in an elliptical path, considering sun at the focus, and for the ellipse the planets are moving in an elliptical fashion, wherein the sun is at the focus. The second thing is the line segment joining the planet and the sun. So this is, let's say, the sun, this is, let's say, the planet, and the line segment joining the planet and the sun. So there is a line segment that joins the planet and the sun. It sweeps out equal area during equal intervals of time. Let's say the planet is here, after some time the planet reaches here. So the area that it sweeps during equal interval of time, the line segment joining the planet and the sun sweeps out equal areas during the equal intervals of time. That means this is an equal area, then after some times the area that the planet covers would be the same as the previous situation. That means aerial velocity of the two is constant. That means the derivative of this part is constant. This is the second law of Kepler's. Then the third law of the Kepler's, it states that the square of the orbital time period is directly proportional to the cube of the semi-major axis. So let's say this is sun and this is the planet, and you have a distance between the sun and the planet, and there is a particular time period. So what is that time period? That time period is orbital time. That orbital time square is directly proportional to the cube of the semi-major axis. So let's say this is the major axis of the ellipse, and half of the major axis of the ellipse is denoted by this a term. The square of the time period is directly proportional to the cube of the semi-major axis. So this is the third law which is associated. Now what happens? There is a numerical problem associated with the same, and that numerical problem I have taken from the book, and it says that the satellite A is placed around a planet and it has a period of 21 days. So that means there is a satellite which is placed on a planet, and the period of the satellite is 21 days, period of rotation. And then the satellite B is also placed in an orbit, but it has twice the radius of satellite A. So satellite B has the radius which is twice the radius of satellite A. Now they are asking for what is the time period, or what is the time period of the satellite B. So what happens here, when the time period and the distance associated comes into picture, that means we have to use a mathematical expression, and that mathematical expression is given by Kepler's third law. And what is that mathematical equation? It says that the square of the time period is directly proportional to the cube of the semi-major axis. That means if I take these two as 1 and another part as 2. So T2 square is directly proportional to A2 cube, and I need to divide them with the keeping them equal with the help of a constant. What do I get? I can cancel them out and I'll get this expression, which is R1 cube over T1 cube, T1 square. Similarly for R2 cube over T2 square. It is mentioned in the question that the time period for the first satellite is 21 days. So T1 is 21. So I need to substitute 21 here. And also it is mentioned that the satellite B is placed in an orbit which has twice the radius of the satellite A. So radius of the satellite is indicative of the semi-major axis. That means we have this R as a semi-major axis only. So the semi-major axis for the second satellite is 2R. So I have substituted this in the expression, or you can use this term as 2R1. So R1 cube and R1 cube gets cancelled out. On solving, you are only left with two unknown variable, which is only one unknown variable, which is T2. So on solving, you will get this value of T2, which is 59.4 days. So what happens with the help of this, you can find out if you have the time period of one satellite. So you can easily find out the time period of the another satellite which is placed in the same orbit. Now coming to the part which is satellite maneuvers. What is this satellite maneuver? This is basically an application of the same topic. So what happens here, when in this particular situation we always require to change the orbit of satellite from circular to elliptical. This is called as satellite maneuver. So when we release the satellite into an orbit, and here it has a condition that simultaneously we want to switch or change the path of the satellite from circular to the elliptical path. That particular situation is called as satellite maneuver. Now what happens, you have an expression which is associated with the same. Let's say E and I are the two energies. One are the energies, and this L indicates, sorry, this is L. L indicates the angular momentum. So this indicates energy, initial energy and the angular momentum, and simultaneously E dash and L dash are the next parameters. Next parameters means the next set of energy and next set of angular momentum. Here this energy is equal to minus C over A, and A here is having this expression, which is A divided by Rp, which is 18 into 10 raised to the power 6 divided by 7.5 into 10 raised to the power 6. So on solving, I will get an expression which is 12 divided by 5. So in place of this E, I can substitute in this expression, I can substitute this value, which is 12 by 5. So in place of A, substitute 12 by 5 Rp. So A equals to 12 by 5 Rp. So I can substitute this value, I will get an expression for E, where R is the radius of perigee and this R is the radius of new circular orbit. Let's say we want to change the orbit or the shape, the path of the orbit from circular to elliptical. So for that situation, we need to keep on changing the value of radius. Now energy associated is related to these terms. First term is this kinetic energy part, which is half mv square. Another term is L square over 2mr square, and the third term is minus C by R, which is this set of energy. So at perigee, V is 0 and R is equal to Rp. Rp is that value of radius that we want to find out. So when we substitute this value, we will get the expression, which is E as minus 5C over 12 Rp. This we have substituted. Velocity is 0, so this part becomes 0. L square over 2mr square minus C by R. So this expression we got till now. Then what is this I square indicative? So I square is having this expression for you can say for the changeovers of the orbit. So I square is 7 by 6 cm Rp. For the circular orbit, we can have this situation. For this elliptical orbit, we had this situation. So for elliptical or the circular orbit, we have this formula which is E dash, the new parameter, which is minus C by A, and A here is 2 rp. So same, in the previous situation we got an expression for E, now in this situation we have an expression for E dash. So E dash, as you know, is having the three components, which is half mv square plus L square over 2 mr square minus C by r. Here V is 0 for the circular orbit because the distance or the radius is constant. That means the velocity part would be the derivative of that constant, and that would be 0. So on substituting, I'll get the velocity part as 0. So I'll have those two components, which is L square by 2 mr square minus C over rp. So on solving, I'll get this I dash, which is Cm rp. So that means I'll have this two expressions. One expression is this E, which is minus 5 C over 12 rp, and here I square is 7 by 6 Cm rp, and another set of parameters, when I wanted to change it, it would be E dash and or L dash. So E dash and L dash, two different expressions. So what I have done, with the help of these two expressions, the radius of perigee can be changed, and this orbital change or the orbital shift can take place from one particular path, which may be an elliptical path, to the circular path. So this is the expression for the satellite maneuvers. So here, as far as this expression is concerned, E is greater than E dash and this L is greater than L dash. So we must give a thrust at the perigee so as to change energy and angular momentum. So what is to be done? By applying the braking thrust at the tangential direction, it will change the parameters, and it will also give the radial directional changes to the energy. But this does not change the linear momentum, as I have told you that this linear momentum is conserved. So by changing or by applying these set of new parameters, that is by giving a thrust at the tangential direction, we can no doubt change the path of the satellite, and that situation particularly is called as the satellite maneuvers. So with this, we come to the end of the video, wherein we learnt about the satellite maneuvers and also we learnt about the Kepler's laws. Thank you.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box. If you found our video interesting, please like, share and subscribe, and do not forget to press the bell icon.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.